two talks today on augmented reality. The third talk that I'm giving today was originally the Google App Engine talk, which I gave yesterday. It somehow got duplicated on the schedule. So we've decided to make the augmented reality talk two talks and talk a little bit more in depth about each one. This talk is about augmented reality that is location-based. So I think there are two primary categories of augmented reality for the mobile developer, and those are location and computer vision based. So the first one we're going to talk about today is the location-based one, and that's where you figure out where the user is, what the device's orientation is, where their camera is pointing, and what's out there, points of interest, for instance. So we're going to talk about some augmented reality basics. We're going to use some very recent sample code from Apple, frankly because it's better than the sample code that my friend and I wrote before Apple wrote theirs. So the idea is that live video fills the screen, and we figure out the device's location versus the location of a series of points of interest, POI. And then we figure out the device's orientation versus the location of those points of interest. So if I am the iPhone and my camera points this way, and I care about something over there, as I turn this way, I'm showing video. They're taking pictures of me now, aren't they? And then once that point of interest gets into the field of view of the phone's camera, it shows that point of interest overlaid on the screen. So the iOS augmented reality stack is in three parts. There's AV Foundation, which is an API that we use for video input and output. We can also use it for audio. So if you want to get the input stream from a camera or from the microphone in the little earbuds or the microphone in the phone, you can use AV Foundation to get it. And then if you want to push that information to somewhere, say the screen in the case of the camera, you can use AV Foundation to either grab those pixels and do something with them. There's some interesting and very useful sort of shortcuts to be able to get that video just directly to the screen, and a few other things that we'll talk about in the second talk, where we talk about using vision-based augmented reality. The second part of the iOS augmented reality stack is Core Motion, in which we use the accelerometers and in the newer phones gyroscope to figure out the orientation of the phone relative to gravity. The third part of the iOS augmented reality stack is the location manager. So the first thing we're talking about is getting live video with AV Foundation. So AV capture session has both AV inputs and AV outputs. AV inputs can again be video or audio, and AV outputs can also be video or audio. We'll show you some sample code. I'll show you some sample code in a moment. And also the AV inputs can be the cameras on your shiny new iPad too, so we can do augmented reality with larger devices now, which was very exciting to me. And the very simplest way of getting video onto a screen live from the cameras is from the AV Capture Video Preview layer, and that goes into a CA layer that you can display on your screen, and you can animate it just like any other core animation layer. Raise your hand if you know core animation or if you've used core animation. Cool. So core animation, briefly, is the means by which we can very easily put things on the screen and animate them. All of the cool effects that you see on the iPhone, or most of them, are written in core animation. Core animation's backend is OpenGL. It's kind of a 2D, 2.5D, which means 2 dimensions plus depth API that underneath is OpenGL, so it's very fast. And CA layer is the basic building block of core animation, where you have something that you're drawing inside of. That is going to be hard to see, isn't it? Who can't read that? Raise your hand. Basically everybody in the back. Okay, so here's what I'm going to ask. If you don't mind, if you can't read that, can you move forward? We've got some room in the front. It's okay, stand up. Come on, move forward, it's cool. I've got time. There's going to be quite a bit of sample code on here, and it's rather difficult to zoom in, unfortunately, in Keynote. So if you're having troubles reading, come on, move forward, it's cool. On the iPhone, we instantiate an AV capture device object. there are default devices for each media type. And in the case of this particular code, we have, does it have a laser? Ooh, it does. Cool. So there are default devices for each media type. So an AV capture device, default device with media type, AV media type video is going to be the default camera on the phone or the iPad, and that is the rear-facing camera. You can choose which camera that you want. I'll show you how to do that a little bit later. And then you allocate an AV capture session. What an AV capture session does is it essentially routes video within your application. So you get an AV capture device input, which is essentially the input from the camera. So you initialize it with the camera. And then the capture session, you add a new input. So the capture session is the central routing device that you say, we have a camera, we use it as its input. And then in order to create a simple, quick and dirty video preview layer, which we can throw on our application, we then use, where did it go? Capture layer, AV capture, video preview layer, init with session, capture session. And so capture layer is in the class I'm going to show you an instance variable, I think. Yeah. That we will put on the screen, and that will show the live video preview. So essentially what we're going to do is we're going to take this video input, we're going to route it through the routing thing, and then we're going to show it up on the screen in a layer. And then there's a little bit of housekeeping that we do here in order to put the layer on the screen. And then what we do in order to start the capture session is we use an asynchronous dispatch to get the capture session running. And the reason we do that is that the capture session will block, the start running call will block, and we don't want to freeze up the UI. So we dispatch that asynchronously so that we don't block the main loop. And then to stop a camera preview, we simply tell the capture session to stop running. We tell the layer to remove itself from its super layer. We then release the two objects, and all of our memory woes are gone. So in order to pick a specific camera, if you wanted to show the user's face to them, for instance, should have done white on black for all of these, shouldn't I? Note to self for next time. So AV capture device, devices with media type, AV type video, and then what you do is you iterate the devices, and you say, I want the device with the position, AV capture device position back, and that's the back camera, and AV capture device position front, which for some reason we got an extra thing there. Pretend that little bit of text isn't there. We'll give you the front camera. So back camera is the one with the side on the side of the device that has the apple on it that's pointing outward, and the front camera, AV capture position front, is the front camera. So if you want to take a picture of the user's face, for instance. So okay, that's how to get the camera. Now we've got to figure out where the user is. So there's a call location framework that allows us to fire up the GPS and get lat-long coordinates, among other things. There's a CL location manager, and it has a delegate. The CL location manager delegate is fairly long. These are the two sort of most often used callbacks. There's a location manager did update to location from location. So what it's telling you is where we moved to and where we were last time. Useful bits of information to have. I know it's a little bit weird to have the from location, but when you think about it, it's nice to be able to say, oh, they're heading in this direction, and then the easiest way to get that is to take the two locations, do a little bit of trigonometry, and say this is their heading. And then the location manager did update heading. If your camera, or if your phone, I should say, has a magnetometer, you can figure out the magnetic heading, and this is what we'll use in addition to the location of the device to figure out which way the device is pointed and where the user is. And once we have those two pieces of information coupled with the information of some point of interest, we can then triangulate, okay, where is this thing relative to me? And more importantly, relative to the direction that the camera is pointed. So in this augmented reality code, there's this thing called AR view. And if you want to download this, I should have mentioned this before, if you go to Apple's developer site and you look for PARK, P-A-R-K, let's see here. If you go to Developer, iOS 5, Dev Center, I have to log in to get to sample code. Once I've done so, if you go to sample code and you search for Park, P-A-R-K, you will find the code that we're talking about today. I'm a member of like 10 teams now, which is kind of fun. Sample code. There we go. So that's the augmented reality sample code from Apple that we're going to be talking about. So in order to get the device's location, very similar to the way that we started up the camera, we have to start up the location manager. So if there used to be a location manager, we release it, and then location manager equals CO location manager alloc init. That gets us an object that will tell us where we are. And you tell the location manager's delegate is, in this case, self, or the object that we want to know. That will get those callbacks from here. So we can implement these two callbacks, and then we can get the location of the device, and we can get the device's heading. So fairly simple. The distance filter is, I believe, in meters. So the idea here is to keep from burning the user's battery up. So if we move 100 meters from where we used to be, it will then call us back and say, hey, you moved 100 meters. It will cause the GPS to ping the satellites less, not ping the satellites, but grab satellite information less often, and will save the user's battery a bit. And then we say, location manager, start updating location. So it will tell us, it will call us back when the location has changed. It will also call us back when the, not the orientation, but the heading has changed. And to stop it, we tell the location manager to stop updating the location and then release it. And again, location manager is a CO location manager object that is an instance variable. So this is one of our callbacks. So location manager did update location from location. This is usually going to get called fairly soon after you start the location manager. And anytime you move within you move 100 meters from where you were, or it thinks you moved 100 meters from where you were, and we'll get into some of the inaccuracies in this and later. We then have another instance variable called location. That's the device's current location. We retain the new location, and then we'll update our place of interest coordinates, and we'll talk about that in a little bit. So the third part, core motion. So in order to figure out the orientation of the device, we need to know which way is down. To know which way is down, we use a CM motion manager. CM motion manager is a very useful object that allows us to not have to do any math, essentially. So what it does is it aggregates all of the information from the accelerometer, from the gyro, and from the magnetometer, and it does some nice things to smooth that data for us, and what we get is a fairly accurate picture of gravity. And if we know which direction gravity is, we know which way down is, we also know which way up is, and which other directions there are, because we also have the compass information. So the nice thing is that new in iOS 5, we have the ability to get an attitude that is referenced to true north. True north is the North Pole instead of the compass north, which is off by 13 some odd degrees, at least in New York. So the idea is that we go, we create a motion manager with CM motion manager alloc init, just like we do everything else. Motion manager is, again, another instance variable of this class. And then we say, shows device movement display. That's the thing where if it's got interference, because we get a lot of interference with the magnetometer, there's magnetic fields all over the place, and you have to move it around to get the map to figure out which way you're really heading. It will actually show that little thing that says, hey, move me around, that little sort of infinity symbol. And we say, every 1/60th of a second, which is about how often the screen is going to refresh, we say, tell me the device's motion. And then again, new in iOS 5, we have the ability to create a reference frame relative to true north with Z being vertical. Then just to stop the device motion when we want to clean up, we just say, hey, stop device motion updates. That will stop the callbacks, and then we can release the object. So this is a little bit more information about this new, very, very useful, because it used to be very difficult to figure out which direction the the device was pointing, or not so difficult, but you know, I'm a programmer, but I don't like doing too much math if I can help it. So what it does is it describes a reference frame in which the z-axis is vertical and the x-axis is true north. So see in device motion object, and I'm not going to read that to you, I promise. This is in the Apple documentation. The idea is that it takes, again, the accelerometer data, it takes the gyroscope data, and it takes basically all the sensor data on the phone that might give you the orientation of the device, aggregates it for you, does some nice data smoothing. In fact, it doesn't actually have to do very much data smoothing because the messiness that's in one offsets the messiness that's in another very often. So there are a few other things that we need to know about how the code works before I try to build and run it and show it to you, which could be kind of interesting. There's a thing called CA display link. What CA display link is in the CA is from the core animation framework. Anything with CA in front of it is core animation. That will fire a method every time that the display updates. Very useful in a lot of different code, very useful in some OpenGL code, also very useful here in that we don't really care to move the position of various labels and stuff except on on display refreshes. And so in order to do that, we use a CA display link object, which I didn't show you how to make one. I'll show you in a second on the sample code. But the idea is if you look up the documentation for CA display link, you can very easily find out when the screen refreshes, and that's when you can move stuff around on your screen. And having the device motion update every 60th of a second, as long as we don't do anything too crazy in the processor, which we don't in this case, it's about how often that the display is going to get updated. So we get more or less synchronized updates of the orientation of the device and the display. So CM attitude object, it represents measurement of attitude. So the orientation of a body relative to a given frame of reference. And that's a kind of fancy way of saying which way the phone is relative to something else. In this case, we'll end up using the Earth. And I'm just going to skip that for now. So inside of the direct of our augmented reality view, we have to do a little bit of fun. So we have to do a little bit of matrix multiplication. I won't go into the math here. Essentially, if any of you have done OpenGL to do camera transforms to figure out which direction to move the camera, that's what we're doing here. So a place of interest, and I should show you what that object is before I talk about it. There we go. So a place of interest is simply an object that holds a CO location. CO location is a bit fancier than what I'm about to say, but essentially is the latitude and longitude. And then the UI view that it's going to be loaded into. So it's a simple way in this application. I'm getting a little feedback. Test. It's a simple way in the case of this application to be able to marry a view with a location. So essentially that's our point of interest object. And so what the application does is when it loads up, it creates a series of places of interest, few in Western Europe and a few in the US, so I'll show you in a second. And then once it has those places of interest, every time that the screen refreshes, it takes the current orientation of the device, does a little bit of trigonometry, which we'll kind of gloss over if you want further explanation. I don't know if I'll be able to have time in this talk to talk about it, but you can come up to me later. And then what it does is it takes each one of those, iterates through them, figures out the relative distance from the user, and then paints them back to front. So the furthest away one is, painted first, and then it puts them on the screen that way. So if you happen to be pointing toward, say, the Eiffel Tower in Paris, and there's also something between Paris and you, it'll take the Eiffel Tower label, draw it first, and then draw whatever else that you're interested in. So whenever we get a refresh of the location of the device, we have to figure out where the places of interest are relative to the device. Once we figure out where the places of interest are relative to the device, we figure out the direction that the device is pointing. And once we figure out the direction that the device is pointing, we know whether or not it's on the screen. That makes sense. So we have a couple of frames of reference that we use to do that. We have latitude and longitude, which is the location coordinates from the point of interest. And then we turn that into an ECEF coordinate. And I'll show you what those coordinate systems are in a second. And then we convert that coordinate system to another coordinate system that gives us the relative direction of the thing that we're pointing to. So ECEF is Earth-centered, Earth-fixed coordinates in relation to latitude and longitude. Essentially, it is a fixed coordinate system relative to the Earth using lat long. Simple Cartesian coordinate system. So then we can do a little bit of matrix. Oh, there, that's what it looks like. Probably glossed over that a little bit too fast. Anybody's still writing stuff? If you want, Wikipedia/ECEF, I think, is where I got this. So basically, fixed points relative to the surface of the Earth. And once we have them in that coordinate system, we will convert them to local east, north, up coordinates. So north is up. And once we have that, we know where the thing is relative to us. And the link is on the bottom there. So the idea is that the local coordinates are formed on a plane tangent to the Earth's surface, fixed to a specific location. And the math to do that is fairly simple, and you can find that on Wikipedia. The code is harder to read than the actual math. So that's where we get these two. And then all we do is we figure out its distance by, a squared plus b squared equals c squared, and then we order our distance back to front. After that and before that is some housekeeping. After it is a bit of sorting to get back to front. So best practices for augmented reality. I'll show you this running. I may have to show some folks afterwards because we'll be running on a device and it's difficult to show that with that. So best practices for augmented reality. It's unfortunate, but you should try to avoid tagging a near object. The inaccuracies in the GPS especially compound as you near target, especially if you're in a large city with very tall buildings. GPS, as you know, is a time solution-based coordinate object tracking doodad. And so what happens is that you've got the signal that's coming at you, and if there's a very tall building right here, and you've got a GPS satellite bouncing its signal off the building to me here, it'll actually think that I'm over-reflected on the opposite side of that wall. And so what happens a lot of times in the places where augmented reality apps are most useful, namely cities, they work the least well. You can check the altitude and location accuracy. For instance, the iPhone can't get good altitude without a good GPS fix because for the most part it uses cell towers to do what it's doing without a good GPS fix. And there's a documentation on the accuracy, and if you find that the accuracy is -1 for altitude, it's basically telling you that it doesn't know. Be aware that the broad side of the barn is easier to hit. It's kind of an Americanism. When you're trying to aim for something that's a long ways away and that's big. So unfortunately right now augmented reality doesn't so much work if you're trying to tag, say, a near restaurant, But it does work pretty well if you want to tag a landmark that's, say, half a kilometer away. So this kind of technology and this kind of application actually works quite a bit better if you care about things like landmarks. So tourism apps, for instance, are very good for this kind of thing. So the bottom line is, unfortunately, here isn't quite here yet. The accuracy of the GPS in particular in these cellular devices, because they have to use cell towers to hint their location, and because they're just trying, well, the reason for it is that the GPS can't take too much battery power, and in order to get a low-power GPS, you have to do a whole lot of tricks to get sort of accurate, but you can't get quite perfect, which is why our applications for turn-by-turn driving are sometimes way off. So I'm going to do a quick demo of, first, the Park app. I'm not sure how well this is going. So like a switcher. Try not to get feedback. Do I demo? Let me get this running on here. In my next talk, I will talk a little bit more about some of these APIs. The one I'm going to talk about the most in the next talk is the video capture API. So how many of you have used the video capture APIs? How many of you have used it to get actual video data and do something with it, like pull out pixels? Cool. So if you come to the next talk, you'll find out how to pull pixels out of the video stream, how to process those pixels, and how to use some computer vision algorithms to figure out what's in those pixels or what's in that image, which will be kind of fun. So let me get this code running on this device. So it takes a few seconds for the camera to warm up, unfortunately. There we go. Let me see if I can show this to you. So the first thing it does is it finds, it creates a series of points of interest. And of course I can't do two things at once. So let's see if I can get this to show. Anybody feel strong and want to help me lift this thing up so I can point it this way? Can we point the camera out this direction? Is that possible? All right. Yeah, I do want to carry with you. So what it's doing is it's taking those, thank you, those coordinates, taking those points of interest names, figuring out the direction to them as I just showed you, and then it's just creating labels to stick up on the screen in the right location on the screen relative to where those things are. So I was going to do a quick demo. One of the things that this particular example doesn't do is it doesn't really pay a lot of attention to the orientation of the phone. So when I hold my phone up and it's in a vertical orientation and I've got these labels, they stay horizontal relative to the horizon as I do this. But if I were to take my phone and go around like this, they kind of get locked up after a while. And that's because the way that we're doing the geometry on this thing is we're kind of assuming that down is more or less, down where the home button is. So I've written some code that I tried to upload today on the network connection here. It's not so much working. I'll give you my email address after this if you're interested in it. It's an OpenGL ES application that uses core motion to essentially put us inside of a 3D sphere. So if you remember those little ball compasses, my grandfather had one on his dashboard to figure out which direction he was going in his car. You can imagine being inside of it. So what I have is a 4x4, actually just a quad with a series of lines in it at equidistant. And what it does is it takes that quad and it wraps it around vertices that describe a sphere. And then it takes core motion and rotates that sphere based on the orientation of the device. And so the neat thing about core motion, or one of the neat things about core motion, is it'll actually give you the transformation matrix that you need to use to do that. It's sort of free out of the box. And I'll see if I can find it in the code to show you in a minute. But the idea is that we're going to modify the rotation of the sphere about the down vector, in other words, towards gravity, in order to get a sort of real world, I'm moving inside of a compass. Stand by. I'll upload when I have a better internet connection, and again, you can email me for access to it. I'm sorry I don't have a link for you right now. It took about 20 minutes before I gave up earlier today. We have a GL Compass view controller, which has an Eagle view. Who's used OpenGL ES on the iPhone? So who's used OpenGL ES 2 on the iPhone? Cool. So very briefly, OpenGL ES 2 gives us a programmable pipeline. So the original iPhone and the iPhone 3G have a fixed function pipeline, and it uses OpenGL ES 1.1. And what that means is that the way that the video card functions is fixed. You can't modify sort of what it's doing under the covers. Whereas in OpenGL ES 2, you have the ability to actually program the pipeline, and so you can throw pixels anywhere you want to, and you can do neat things with vertices, and you can do it all inside of vertex and fragment shader programs. Who knows OpenGL 2? Regular OpenGL 2. Cool. So in the iPhone, we have this thing called an Eagle view. It's just the sort of GL view that it actually is something that is in a whole lot of Apple sample code, and pretty much everyone uses it to do OpenGL stuff. It's also part of the OpenGL regular sort of default project. And so what we're doing with this compass view controller is we're creating an OpenGL view, we're stretching it across the screen, and we're doing some of the same things that we do in Park. So we're figuring out the direction that is down. We're drawing, in this case, a sphere with a bunch of lines, but you can see that if you have a sphere with a bunch of lines that indicate your indicate direction as well as altitude and azimuth, you can easily put stuff on there that is relative to other stuff. And then what happens is instead of having to hold your phone this way, you can hold it any way that you want, and the sphere just sort of rotates around you. Unfortunately, I'm just going to have to describe it to you. Well, actually, I think I might be able to show that. Updating about 60 times a second. You can see these lines. Right, so that's just an image that I drew. And I get a little bit funky at the bottom because of the way the vertices work, so don't worry too much about that. See how far up I can get it to go. You can see that that is holding stationary relative to the real world, and we've got sort of the south pole of our compass down there. And again, access to this is by email as soon as I get to a real internet connection. Slides. Talks later today. I'm going to talk about optimizing data caching for iPhone app responsiveness in, I think, room B. I forget. It might be A. And so what I'm going to talk about there is how to do some drawing in the background thread, which is supposed to be a no-no, but there are some ways to do it. How to stay off the foreground thread when you're doing data caching and such. And then sort of part 2 of this talk is computer vision and vision-based augmented reality. So the first kind of augmented reality, which we just talked about, is the geography-based augmented reality. Vision-based augmented reality takes an image coming in from the camera, figures out what's going on inside of that image, and does cool stuff with it. So for instance, you can take a marker and put something on top of it. So with that, I open to questions.